computer science at the University of Michigan. He spent many years at Austin.
Austin, Texas.
Yeah, and he got his. He's a very distinguished AI researcher. He's an AAAI and IEEE fellow, and has been working in this area for many years. And his roots go back to his academic roots go back to MIT. Yes. And well, this was with.
Yes, my advisor is Marvin Minsky, actually. So.
The very roots of AI.
Yes.
Okay, so his tutorial is on multiple spatial equalities in humans and robots, and I believe he will focus quite a bit on how we can cross the different levels of representation from the lower level to the higher levels, and tell us about his work.
Yes. Well, thank you very much. It's a great pleasure to come here and to talk again. In fact, what I'm going to do is talk about two separate but closely related topics. So the first half of the tutorial is really going to be dealing with the spatial semantic hierarchy. What is the structure of knowledge of large-scale space? Excuse me. And then the second half deals with a separate question, which is how can an agent learn the foundational domains, where I consider the knowledge of space to be one of the critical, the most foundational of foundational domains, if you don't have that knowledge given to you in advance. And so how can an AI be created without intelligent design, if you will? So we'll talk about that after the break. Now I've arranged this so that there should be plenty of time for questions and discussion. So feel free to raise issues, and we can spend a little time dealing with some of these things. So one of the things that's pretty obvious and was very striking when I first started looking at this is that humans have cognitive maps. And human cognitive maps have a lot of very interesting properties. And one of them that was particularly striking is that humans use multiple representations for space. So one kind of knowledge that you often see is that people know how to follow a route to get from one place to another. I know how to get between my hotel and this place and back again, and I've been exploring multiple routes. But I might not have a metrical map of that same area. I might simply have the way different places are connected. Now, in fact, some people don't even have a real topological map. They just know when I see a particular landmark or something, then here's the decision I take. But some people do build metrical maps. So a particularly interesting thing is people have topological maps. Some people have metrical maps. Most people actually build topological maps. Some people don't. The interesting particular thing is that individual variation is really everywhere here. And that includes variation as children grow up, as one learns an environment, and of course with just individual style. A particularly striking piece of work, which I recommend everybody read. This is a small, delightful book by Kevin Lynch called The Image of the City, published in 1960. And how many of you have read it? Nobody. Oh. Go out there and read this thing. It's really interesting. And of course, Piaget looked at knowledge of space and made a lot of really interesting, important observations as well. Now, when I got into AI, one of the things that was particularly striking is that the computational methods that I encountered when I first encountered AI were the first things that actually held out the prospect of building models of the mind, building models of mind that were capable of doing what the mind does. Because when you think about explaining the mind is fairly clearly an information processing process. And if you understand how it works, it really only makes sense that the model should, in some sense, be able to carry out the task. It should actually think. And so in particular, if a mind is supposed to be dealing with the environment, it should be able to move through the environment, gather observations, build a model of that environment, and navigate. And since what we've seen is that the human's knowledge of space includes multiple knowledge representations, then our computational model had better have multiple representations too. So part of what this implies is that we really need to have perception in action. So the model has to be grounded in this kind of interaction with the world. Much work in AI at the very beginning was sort of held the world at bay. And you would either simulate perception in action, which is what I did in my PhD thesis, for example, or solve problems that didn't really require perception in action. But if you really want to take this kind of knowledge seriously, you need a computational model of perception in action, and that is pretty much by definition a robot. Simulated robot maybe, physical robot if you really want to make sure that you're being honest about how you're dealing with the perceptual and motor world. Now, there's a couple of conceptual distinctions that are actually going to be important here. And I've referred to these before, but I want to really spend some time on them. Small-scale space is, I define as space within the agent's sensory horizon. So the space within this room is something that I can explore by simply shifting my point of attention. So I can shift my attention around almost instantaneously throughout this room. But the structure of the city is large-scale space, so its relevant structure is well beyond the scale of my perceptual horizon, so I have to knit together information gathered over time. Now, from a methodological point of view, one of the things this means is that I have states of partial knowledge, states of knowledge that are intermediate steps on the way to building a more complete knowledge representation, and I have to preserve those over significant periods of time simply as I walk along the road. So it can take minutes and minutes, and there are intermediate levels of knowledge that are there to be looked at. And so from the point of view of being able to talk to subjects, get them to draw maps, get them to solve problems, those intermediate states are much more accessible than they would be, for example, the intermediate states of understanding this, this room. Because I gather a bunch of visual images over a few seconds, and those intermediate states come and go within milliseconds or hundreds of milliseconds. So it's actually quite more difficult to get a hold of those, and they require more difficult experimental methods. The other distinction I want to make is between ontologies, which is, I use ontology the way AI people use the word ontology, which might be sort of working a little fast and loose compared to how the philosophers would. And what I mean are the categories of objects and the types of relations that are defined. So it's what can you say? What is there and what can you say about things in the world? And so one relevant ontology is metrical mapping. And so when people first come into this question of spatial knowledge, people think of metrical maps. And a metrical map is characterized by a single geometrical frame of reference in which you can define locations, headings, pose, distance, shape, things like that. One of the things that's obvious but often escapes notice is that if you're drawing a map on a piece of paper, the piece of paper has a single frame of reference. Every time you put a new point on that piece of paper, it inherits a relationship, a spatial relationship with every other point that's already on that map. And so it's quite clear that's not something that's true of cognitive maps. So you learn a new place and you have a relationship perhaps with the previous place that you visited, maybe with a couple of nearby places, but not with some other place that you had visited yesterday, for example. So that's one of the ways to make a compelling case that knowledge like that is represented topologically, where we have places, paths, and regions that are related by sort of set theory kinds of relationships, like connectivity, order, and containment. So we're building graphs and containing sets. And so these are two fundamental distinctions that we'll be using. Now, over the course of time, we developed a couple of different but closely related spatial semantic hierarchies. And what I mean by a spatial semantic hierarchy is, first, obviously it's about space, and in particular, mostly about large-scale space, but it also is a hierarchy of multiple representations. It's not the same as, for example, a hierarchy of places and regions. Like we could say, I'm in this room, I'm in this building, I'm in this neighborhood, I'm in this city, I'm in this country, I'm on this island of Great Britain, I'm in Europe, and so forth. That's not the kind of hierarchy I'm talking about. I'm talking about a hierarchy, as we'll see, of representations. And so I want to focus first on the basic spatial semantic hierarchy, and we'll move on to the hybrid spatial semantic hierarchy. The basic spatial semantic hierarchy started with this notion that perhaps I don't even know what my sensors are sensing or what my actions are doing. Nonetheless, if I know enough about them to define control laws, then I can define places, I can define connections between things, and I can build up from there. And this question of how do you come up with those control laws and how do you use that is something that we'll be talking about after the break. But here we're going to assume that suppose we have a certain number of control laws. And so this requires very weak prior knowledge on the part of the agent. All we really need are hill climbing control laws, and we'll have trajectory following control laws and distinctive states, which I'll talk about in a moment. So there's a key notion which helps us go from the pixel level view of the world, that is, the representation of the world in terms of small sensory elements. And I use pixels kind of metaphorically, not just for visual pixels, but for any small sensory element, and even for small motor elements. So suppose I'm somewhere or another, and I can follow a trajectory following control law, like follow the left wall. Here I'm moving along, keeping an approximate distance from this left wall, and I get to a certain point where I can detect that things have changed. In particular over here, what's changed is that I'm close to this other wall, And so if I can detect that I'm now within the basin of attraction of some hill climbing control law. For example, in this case, I'm going to move so that I'm approximately equidistant from the nearby obstacles. Then the local optimum of this, or the fixed point of the hill climbing control law, is what defines a distinctive state. So now suppose I want to go back. So now I'm going to follow the right-hand wall for a while. Now, as we see here, there's a certain amount of error. Any action on the part of a robot is going to have some sort of error. I get into this basin of attraction of this distinctive state, and so I hill climb and I get to that distinctive state. Now, once I have that pattern of behavior, that authorizes a kind of abstraction to places. So now I have a far simpler model of that area. So this was a continuous world requiring continuous motion and having essentially an infinite number of states. And here I've defined an abstraction that has two states and two actions, one that goes this way and one that goes that way. And so now I'm at something that is far, far conceptually simpler. And based on this, I'm now going to be able to build topological maps. And so this was a really exciting notion that I can start with the behavior of low-level control laws and abstract out high-level concepts, in this case places and path segments. Now, an interesting thing here is that, as I pointed out, following control laws is always error-prone. You're going to accumulate a certain amount of error, but as long as that error is controlled enough so that it intersects with the basin of attraction of the destination distinctive state, then you can hill climb, you can eliminate the cumulative error. You can't eliminate all error, but you can eliminate the unbounded accumulation of error. And as long as you can always end up within that basin of attraction, then you can set off on the next link. And motion at this abstracted level becomes effectively deterministic, even where motion at the continuous level was error-prone. So this is actually a pretty exciting property. So here's an environment where my student and I explored this. And so, for example, you'll see here the robot is going, following the left wall, say, and then it detects that there's a sort of discontinuity here. There used to be open space on its right, and now it's going down a corridor. Now it follows corridors and defines distinctive states around here, and so forth. These little things are dealing with the sort of little loops around some of those distinctive states are dealing with simulated properties like the properties of sonar, which produce illusory openings. Here we notice that you can find the distinctive state corresponding to the same place, but in slightly different physical locations. But those are functionally equivalent, so they really count all as the same place. Now, again, when we have this kind of pattern of travel, it means that this continuous environment can be abstracted to this really very concise graph. So now, if what I wanted to do was to say go from here to there, in the continuous environment, that's relatively difficult. In the discrete environment, it's a trivial graph search problem. And so we find a solution as a graph, but then each edge of the graph can be translated back to the associated control laws and turn into a trajectory that will take you from one place to the other. So this is actually pretty nice. It had a few little difficulties, which is some people would say, you know, this notion of not knowing what your sensors are sensing and what your actions are doing is unrealistic. We really do know in most cases when we build robots what the sensors are sensing. In the long run, you may actually grow sensors, and so there may be circumstances when you don't know the actual properties, but we mostly do. Yes?
So it seems to me the main danger is that there's sufficient noise in the movement between these distinctive states.
Yes.
You actually miss the target. And
Yes.
you're lost because you don't know where you are.
Yes. So, for example, if you started out here and got enough noise that you missed this entirely, then you could have a problem. Yes. So it does require that your error is not growing too rapidly, or that you have ways you can actually overcome this to some extent by saying, well, as I was going down this path, the cross corridor, for example, was small and inconspicuous, and so I might have missed it. And so if I go farther than I thought I needed to, and I end up at a place down here, for example, that has a different local structure, then I could explain that by saying, well, obviously I missed the place I should have seen first.
This reminds me of cruise missiles in my campaigning days.
Yes.
In how cruise missiles work, and they look like this. And,
yeah.
And they also can miss the target. So if the,
yes.
the target being a way station, that
yes.
they recognize and reroute themselves
right.
on their journey. And then that can be pretty dangerous.
Yes, right, because then it's just heading out looking for something that looks like its destination, and then it'll blow it up.
Yes.
Yeah, one of the things that was very formative in my early years is that after I finished my PhD and spent 1 year doing military-funded research, and I was looking for a sponsor for the next year, the only people who were interested in funding my work were people who wanted to build cognitive maps for cruise missiles and to find somebody's house and blow it up. And I said, you know, this isn't actually what I had envisioned my life's work being for. And so I did a major change in my research trajectory, which actually there's a paper in the references at the end here that talks about that in case you're interested. It ended up being very productive from my point of view, but it was sort of disappointing and a shock at the time. So often we actually do know what the sensors are sensing. And the notion that as I travel, I have to do my hill climbing and get myself physically sitting on this distinctive state also seemed a little counterintuitive, or at least unnatural, because as most people travel, they're prepared to cut corners and move more smoothly. But then I realized, okay, all right, so perhaps we do know these local mapping methods. Probably we should be able to use them locally. And so we created this thing called the hybrid spatial semantic hierarchy. And what it does is it uses this, the ontology and the scale that I described earlier. We look at small scale space and large scale space and metrical mapping and topological mapping. And one of the things that started being developed now perhaps 20 years ago was modern laser-based SLAM methods, methods for simultaneously localizing and mapping. And they just worked like a champ in small-scale spaces. And so we would be able to create excellent local metrical maps and do local navigation in just an outstanding way. And for a while, I thought that was a sort of competitive technology. Then I realized, well, actually, I should incorporate it into what I'm doing because it was so good. And of course, visual SLAM has also been taking off and is now really excellent as well. So, but it has limitations, which I'll talk about in just a moment. Now, the difficulty is that once you can build really good metrical models of small-scale space, it was tempting to say, well, now we can build metrical models of large-scale space. And the kinds of problems that people ran into is that is when you're closing large loops, this is what happens. I mean, the space looks, from this somewhat corrected image, you can get a sense of what the space looks like. But even a very small drift as you're traveling around this creates a major deviation. So the loop that started here terminates here, and you start creating a map which is really incoherent. And with this assumption that everything is being put into the same frame of reference, parts of the map are written over other parts of the map. Now, this is what would now be considered a completely naive way of doing large-scale metrical maps. Shortly after that, people started to be able to use local SLAM to correct the odometry, and you would get much better maps. But as you can see, they still don't match perfectly. Methods were developed to match things better, to start building, detecting landmarks and building graphs of these landmarks with constraints. And so now people can build quite large-scale metrical maps, although it uses, it shares a number of the methods that I'll talk about later on. And I still claim that the way I have parsed these different methods actually is better for an agent in the world. Did you have a question? I'm sorry? Okay, SLAM is an acronym for a method called simultaneous localization and mapping. And it's a Bayesian method for using the local observations to try to build a model, use the immediate observations to build a model of the environment. Then, upon moving, use the observations to correct the knowledge of where the robot is before then using the next round of observations to extend the map. So it's designed to address the problem that you need a map in order to know where you are, but you need to know where you are to build a map. And so there's a mutual dependency here, and by building them in essentially simultaneously, sort of one step at every instant, you first determine where you are, and then you use your observations to extend the map incrementally. And at the beginning, with no observations, you know where you are because you're at the origin. Where else could you be? Yes?
Can you incorporate into the Bayesian prior some default assumptions like the fact that the roads are at right angles, they tend to be straight and so on? I mean, this would work well in New York and Edinburgh, Newtown, but not around here. But,
yes, right.
I mean,
well, if the stronger the priors you put in, the better this would work. The difficulty is that then you're vulnerable to the failures of those priors, and that can be pretty dramatic. And so one of the things that I discovered early on when I started doing cognitive maps is some of the other people who did cognitive maps had done it in New York City. And this had led them to incorporate strong priors, whereas I did it in Boston. And so I had a much more irregular environment to deal with, which I think actually revealed more of the actual structure. So I'm skeptical about strong priors, which is to say. So as you can see, in extreme cases, that the errors can accumulate enough to produce a locally optimal but seriously false loop closure. Now, what we do in our robot is to start by building what we call a local perceptual map, which is local SLAM, no large loops, to set that the robot maintains a bounded fixed size map around itself, which scrolls with it as the robot moves, keeping the agent near the center. The incremental update has constant complexity, and this is designed to be a map of small scale space, so by definition it doesn't contain large loops. It also contains most of the information that you need in order to plan safe and comfortable motion. And we're going to avoid collisions with various objects, and we're going to be able to analyze the local decision structure. So I want to show you an example here. Here's the robot, and it's exploring, it's right about here. This is a topological map that it builds. When it creates those little gateways, it's moving along. You can see it scrolling. It's now reached this. So here's a place. There will be a gateway around here as it leaves. Now when it's traveling, it stays at the center and the map scrolls by. When it gets to a decision point, it moves. It sort of holds the thing constant. When you saw that blue tree all of a sudden flash into and out of existence, that was a Voronoi diagram, and that's used in order to determine the local topological structure of the decision point. So now it's found its way into what is the robot lab that was at the University of Texas, and it's exploring to find out most of that space. And now it's happy. So, so we can do a very good job of maintaining the local map. So this is its situational awareness, essentially. And it's, as it traveled, one of the things you noticed is that there was this feeler that went out, and those were sort of tentative plans that it was making. So that's showing how we do this local SLAM. The next step is to build a model of the local decision structure. So once we can build a local model, then what we're going to do is, given this local model and the robot being in a particular place, then this is in small scale space. It uses the Voronoi graph to get the overall structure. It identifies a set of gateways that bound the local region and separate it from the path fragments that go in various directions. It looks to identify situations when the path fragments align, so that it says these two path fragments here are part of the same path that passes through this place. Whereas this could potentially connect to this one, but it has another option, and so the choice isn't unique. So these three path fragments are considered to stop or start at that place. And so we can abstract this model in local space into this node, which is part of a large-scale space description. So I go through that in a little more detail. We'll see gateways. These are gateways which represent the connections between the local place neighborhood and the path fragments around it. And they represent transitions between trajectory following control laws and the local perceptual map. So first, we identify a change in the structure, basically because, for example, a follow the midline control law is no longer appropriate, and build a model of that local region. Then the Voronoi diagram, the Voronoi graph, can tell us when and how this local region connects to the frontiers, the edges of the local space. At that point, we can identify constrictions, places where there are likely boundaries, and identify a set that, along with the obstacles, these gateways provide a complete boundary for the place neighborhood. At that point, we can focus on the gateways, and when two gateways are well aligned with each other, each gateway is going to be associated with path fragments, incoming and outgoing, and when two gateways are aligned with, this one has a unique continuation and the other one has a unique continuation, then we identify them with each other as being part of the same graph, as being part of the same edge. And this allows us to build a circular order of the gateways and the path fragments. And so here we have a path fragment, which in this case, well, let's take this one, path fragment 2 in the plus direction corresponds to gateway 2 going outward and following the midline. Path fragment 1 corresponds to both this gateway going out and that gateway going in. This is, and here are the appropriate control laws, and that can be translated in a very natural way into the language of large-scale space, into the kind of graph structure that we use for describing large-scale space. And as I mentioned, these paths and path fragments are directed, so they have a direction. Now, this abstraction allows us to, as we plan a route in the large-scale graph abstraction, for example, I might decide, suppose a route involved coming in on path 1 and then going out on path 2. That translates in small scale space into coming into this gateway and then departing at this gateway. So what is described as a simple reorientation in large scale space actually is going to translate into a trajectory through that place neighborhood in small scale space. So we have to be able to go back and forth up and down this abstraction hierarchy, and this allows us to do that. So does a place abstraction always exist? Well, maybe. Clearly, if you're in a totally indistinguishable place like open ocean, you would think that it can't possibly exist. But there's been interesting anthropology with people like the Puluat navigators. This is in a South Pacific set of islands, an archipelago, where many of the islands are over the horizon from each other, but people travel between them all the time. And they'll have routes like, you follow this direction, which is defined with respect to the stars, until you get to the place where the dolphin jumps as the two plovers fly over. So the anthropologist piles into the canoe with the navigator, and they take off, and they're headed for this other island. And after a while, he says, okay, we're there, we're at the place, and now we reorient to take this other heading and head for our destination island. And the anthropologist says, I didn't see the dolphin or the two plovers. And he said, well, I guess they weren't out today. So you have a place that actually has no perceptual properties. And so what that illustrates, to my mind, is that it has representational properties. It allows the person to represent the route as a trajectory and a decision point, and then you make you reroute the heading, and away you go.
I was once in a talk by somebody in geographic information systems, and they were interested in modeling oceans and things like the Gulf Stream and the sea, neither of which have fixed boundaries.
Yes.
And yet there is, there clearly is something called the Gulf Stream, which moves around a lot, it's different shapes at the time. And I thought that was a really challenging representational problem.
Yes.
It's a real AI challenge.
And so what's interesting is it's a little like if you collect data about how people walk through a large square, for example, and you can collect heat maps of where you've observed people, and it will, as you collect more and more data, it resolves into essentially topological paths. And of course they're fuzzy in their boundaries, but there's a path that goes from that entrance to that exit. And people tend to follow this way, although of course depending on who's coming the other way or whatever, the actual trajectory may vary significantly. So it's, these topological things are what function in control theory and dynamical systems as attractors. So it may have a nice clean, abstract location, but in fact, you would sort of wander around in its neighborhood as you're actually following it. So my conjecture is that if you're in a sufficiently rich environment and you have sufficiently rich sensors, which is like virtually every environment we navigate in, then yes, the place abstraction makes sense, and people have a very strong tendency to use it. And it's a very useful thing to have. So now once we can abstract from the metrical properties of local SLAM, of the local metrical space, to the topological local decision properties, we need to knit those individual observations into a global topological map. And this is where I claim in the spatial semantic hierarchy that loop closing problems are solved. Loop closing problems are often treated by the purely metrical mapping folks as metrical problems. But a metrical problem has many, many solutions, usually a continuous space of solutions, whereas a topological problem has a discrete space of solutions. So what we're going to do is create a tree of all possible maps that are, all possible global topological maps that are consistent with the local observations. Now, I'm not going to go through this in detail, but this does actually present the algorithm. Every time you get a new action and observation, if it's already predicted, fine, your map is doing great. If the map contradicts the observation, you prune it, and that shrinks the tree. But if this is a new, there's no prediction and obviously no contradiction, then you have to extend the tree, so you branch on new edges, including all possible loop closing hypotheses, and there's always a hypothesis that you're in a brand new place. So I'm going to run through this. It'll be a lot clearer with an example. So imagine here, we're traveling through this environment in this sequence. And so the local topology is identifying the T intersections, the plus intersection, the L intersection. So when you show up at place 1, you see a T intersection, and so this is what your map looks like. No problem. So now we're going to head over here and we're going to observe another T intersection. And there's two possible hypotheses. One is what we know to be the correct one, which is that second T observation, that second observation of a T intersection is a different place. But there's also the possibility that you're in the Little Prince's world and you've actually gone all the way around this tiny little asteroid and you're back at the same T intersection again. Now, there are ways to exclude this through observations depending on how well you can track your orientation through control laws. And so I'm going to assume that we can exclude that, and I'm not going to spend more time on it. So we're now going to go down the base of the T, and we get to a plus intersection. Whoops. So we get to a plus intersection. There's no possible loop closure because there's no other plus intersection already in the map. So the only possibility is to extend the map, so we've got no problem. So now we go along and we encounter an L intersection. As before, there's no other L intersection, so there's no possible loop closure. So we simply extend the map. So now we go and we encounter another T intersection. And the real question is place 5 the same as place 1? And so we get two hypotheses. So this one says place 5 is equal to place 1, and this one says place 5 is not equal to place 1. So one of the things we do in this tree of maps is each branch corresponds to a commitment to the truth or falsity of that, that match. Now you may ask, well, couldn't place 5 be place 2? Because those are both T intersections. Anybody see why that's impossible?
Because we're going to be left and we can make right for the starting point.
Yes, although depending on these edges, so I've drawn these edges to be straight, but if you would imagine these as taking place in the mountains and being sort of long twisty roads. Now consider place 2. So here's place 2. Now we know what's connected to this edge and this edge from place 2. And so in particular, we know from place 2, the base edge is connected to a plus intersection. So and we know that place 5, its base edge is connected to an L intersection. So we already know something about the global structure of place 5 that contradicts the hypothesis that it could be place 2.
You have to rule out the fact that you didn't pass a 4 on the way from 2 to 3, because you could have come in sideways. The arrow could have entered as a 4 onto the route between 2 and 3, and then you were back on that route again. So the fact that you didn't pass a 4.
Right. Yes. The assumption here is that you would have noticed every, right, that's true. But you would have to not notice it in both directions.
Yes.
So,
That's true. Have you overcommitted by putting that 5 junction to the left of 1? Would it not be to the right of 1? Is the geometry forcing you to make an artificial choice there?
well, no, this is a loop closing hypothesis. So what I'm doing, there's no commitment to the geometry. So it actually could be to the right there. Yeah, that's simply the layout problem that I had in drawing the slide. So now the issue is we're going to follow place 5, and the next thing we're going to observe is another T intersection. Now, first thing I'd like to draw your attention to, within this map, you can see the arrow is at place 5, and so we go one step further and the arrow is over here. So this map is perfectly consistent with the observation, and so it simply stays there. This map, we have two possible hypotheses. One is a loop closing hypothesis that says place 6 is equal to place 1, which would produce this map. The other is that place 6 is not equal to place 1, and we already know that place 5 is not equal to place 1, and so we get this map. Now, we know this is the correct one. We have a couple of ways of dealing, but actually all three of these hypotheses are consistent with the sequence of observations that we've gotten. So this tree, under some assumptions like we can't have missed places, it's guaranteed to contain the true map, because all consistent maps are created and only inconsistent ones are deleted. And each map is a distinct loop closing hypothesis. Now, we can rank the maps by simplicity, and so one of the ways we dealt with that was to do that. Another thing we can do is we can start to incorporate metrical information into this and compute the likelihood of the odometry that we observed given a layout hypothesis that follows from the lengths of the paths. And so that's a method that we currently use. Now, here, this one is clearly simpler than either of these two. And it's also more consistent. I mean, if you were to have metrical information, it would obviously be more consistent with that. So either one of those methods would do it. Now, it is important to remember the best map, to remember the whole tree, because the current best map could actually be refuted. So one of the environments that is very instructive in Boston here is, this is Boston Common. And many people, even long-term residents of Boston, think that Boston Common, just like Boston Public Garden, is rectangular. But in fact, it's a pentagon. And people think that each of these intersections is essentially a right angle, because many of them are, but they're not. And this leads to distortions of the cognitive map in Boston. So what this allows us to do is to build a topological, a correct, or at least a good working hypothesis for the correct topological skeleton of the map. And now the question is, suppose, well, before I go on, actually, let me mention that for many purposes for an agent to navigate within an environment, all you really need is the topological skeleton. Or maybe the topological skeleton labeled with the lengths of the edges and the local geometries of the places. You don't need to put the thing into a single global frame of reference. On the other hand, some people do. I tend not to, actually, so this is one of the reasons I put a lot of emphasis on this. But some people do, and it can be very useful because it can help people find shortcuts. One of the kinds of individual variation that you often see is that some people aren't comfortable searching for shortcuts. And there are several different methods for searching for shortcuts. So what we want to do is to be able to go from the global topological map to now build a reliable global metrical map. And so what we're going to do is we're going to take our topological map, which we can use as a skeleton, lay out the places into a global frame of reference, and then fill in the details from the rest of the information we have. So if I have a map that has a number of places where I have local maps of those places, and I also have the local metrical information about the travel along each individual path segment that says how far did I travel, what kind of angular difference is there between my pose at the two ends, and perhaps how much variation was there in the middle. Now, using that information, we can actually take these places, lay them out more or less arbitrarily, or do a simple initialization, and then use a relaxation algorithm that sort of treats all of those connections as springs, and then just sort of slides these into the optimal positions. That actually works extremely well. Then, once you have the position and orientation of each of the local places, we can then take the recorded individual steps of each of these trajectories and lay them out anchored in the locations of those places. So notice here, when we're creating this layout, we're only specifying x, y, theta, the position and orientation of this map. The internal structure of the map is just slid and rotated there. So when we create this map, it's got a small amount of information about each place and its position and orientation. And what we're doing with the rest of this is we're now trying to fill in the rest of the points. So here are the poses that the robot followed as it traveled through this environment. And given those poses, we can now take the laser observations and build a map of the environment without these cumulative errors. So now we have some very largely correct poses, and we can then make a largely correct model of the environment. Now, if you look very carefully, you'll see that this edge, which in the real world is straight, actually has a slight bend in it. And that's because there is some remaining error in the information you have. And if we continued to gather more observations, we could correct that error as well. So at this point, we can remove the path that the robot traveled, and we get a pretty accurate map in the global reference frame. So what we've got now is 4 different representations for navigable space. And these can be used in the following ways. The local map is really good for planning safe motion. The topological map of local place neighborhoods gives us a set of well-separated decision points that describe what to do, that describe qualitatively what the options are and perhaps what choices are made at particular places. The global topological map is an economical and scalable way of representing the structure of the overall environment. And the large-scale metrical map can be used for developing heuristics for route planning, so that you get from A to B in the shortest way, perhaps. Now, there's also behavior architectures that have been proposed over the years in AI, and these three-tier behavior architectures that are grounded in continuous control and then do task sequencing and deliberative planning, those fit very nicely with the different representations in the spatial semantic hierarchy here. Human-robot interaction also fits very well with this structure. So if you try to collect the ways people give instructions to a taxi driver, to someone pushing a wheelchair, to whatever, there are a variety of different conceptual languages that people are using that map very naturally onto these different representations. So in small scale space, I can say things like go over there, or go to the door, go to the exit. In the structure of local decision points, I can say things like take the next left. Or I can aggregate things and say take the second right, which really refers to two separate decision points. In the global topological map, I can have named locations, and if the speaker and the robot both understand the same locations, then you can specify things like take me to the kitchen or take me to the doctor's office. And on a large-scale metrical map, perhaps you can point to a point on the map and tell the robot to go there. Now, something went wrong with embedding this movie, but I want to show you a little bit using our robot wheelchair. So the robot, when it sees a place, it has identified those gateways, which are essentially navigation affordances. And here, the robot has been, by selecting one of those, the driver has said, okay, let's go there. This, by the way, is the motion planning method. It generates maybe a couple hundred possible trajectories and then evaluates them. And it does that several times a second, and it can make smooth, safe, and comfortable trajectories. And so there, you can make a plan topologically and then carry it out in local small-scale space, and do that in a very smooth kind of way. So this illustrates the decision level interface of the goal level interface specifying a target place is also feasible, but we haven't got that in the movie. So, what have we learned? Partly, we really need to use multiple representations for space. And I would claim that that's a characteristic of a lot of different kinds of common sense knowledge, that we often have to have multiple representations of the same thing. And we can build these semantic hierarchy of representations that make it easy for going between. The distinction between large-scale and small-scale space is important. Although the hybrid spatial semantic hierarchy is called hybrid because it incorporates both small-scale and large-scale space. And the difference between metrical and topological representations is very important. So these are unavoidable, and so we really have to represent them if we want to be capable of doing the kinds of things people do. They're also very useful because with multiple representations, vectors provide information that's more relevant to particular kinds of representations. And as we've just seen, the different representations lend themselves to different communication styles. And one of the things that's also characteristic of people is that people just jump between these different styles. A friend of mine has an example of a single sentence in which somebody jumps between 6 different frames of reference. I don't know it well enough to recite it to you, but it's quite dramatic. And the human example is very, very useful. I think as a heuristic for research in artificial intelligence, it's hard to go wrong by assuming that people are doing the right thing, that people in general have learned how to solve the problems that people are faced with. Now, it is possible to build things that have superhuman performance of various kinds, but you really should understand why people do the things that they do, because often it is necessary in order to have the kind of robustness and flexibility that you want. So here are, let's see, these are a couple of papers on our local motion control method. This is the paper on the hybrid spatial semantic hierarchy. This is sort of the story of my life as a long time ago. But it includes this story about changing research direction. This sort of formalizes the topological maps in non-monotonic logic. And this is an earlier paper that describes the basic spatial semantic hierarchy. And there's lots and lots and lots of papers in here that sometimes elaborate on those, sometimes are precursors to some of those papers. Now, after the break, what I'll want to do is change gears somewhat. Because as you look at this, you see what I'm doing is saying, we know a bunch of things about how we want to represent space, knowledge of space. And so we program it up. We build systems that represent those representations, and we figure out how to translate sensory information from robots into those representations and how to solve problems using those. And it's all great. This is just sort of standard AI. What if you woke up in the world, you're a robot, and you have this big, long sense vector that comes from your various sensors. But you have no idea what the elements of those sense vectors, what the elements of that sense vector are responding to. You have a motor vector. You can make things happen. But you have no idea what actually happens when you send those signals up. You don't know what your body is like. So you are in the control room receiving coded signals without the code. And you don't know what kind of world you're in. So you got a problem. And what makes it worse is you have to figure out how to make a living before Darwin comes and takes you away. So this sounds pretty miserable and pretty unsolvable, except arguably babies have been solving it forever. So where you personally live is in a piece of meat, locked in a box, with long cables of fibers coming in from various places, providing coded signals. You got to figure this out. This seems to me to be the real AI. How do we start Don't touch that dial. Stay tuned. This is what we're going to do after we have this as well. And I've got some time for more questions. Yes?
I wanted to ask you, what's the rationale for not using an metric measurement in the global topological scale?
Not using a what?
An metric measurement. So because there is
Yes.
a tree of possible
Yes.
generalized trajectories, but wouldn't, at least in terms of very basic shapes, wouldn't measuring the distance narrow it down?
Okay, so the question was, I'm saying this for the benefit of the microphone. The question was, why not gather metrical measurements while you are building a topological map? And I agree, that's a very sensible thing. The primary reason for not doing it is expositional, to sort of clarify the distinction between the different kinds of, the different representations. Now, in fact, as we implement the system, we do gather that information. The local metrical information is actually gathered simultaneously with building the topological map. But logically, the metrical information depends on the topological information. So for example, as you travel from one place to another and you make a topological link between them, the place where you store the distance is associated with that link. So in some sense, you have to create the link first so that you have a place to put the metrical observation. So even though creating the metrical labels is actually done interleaved with creating the topological links and nodes, they're sort of logically separated. So in fact, we collect them all at the same time. Yes?
You describe the situation of a newborn baby very well, human baby.
Yes.
But for many animal species, shortly after they're born, they're up and ready to run with the herd.
Yes.
So they must have some kind of interpretive sensory data machinery and also action planning machinery already there.
Yes.
They're born. So that's a real challenge because they haven't really been able to practice up until then. So do you have any thoughts about
Oh yes, absolutely, absolutely. And I think that human babies actually clearly have a bunch of innate knowledge as well. What I do here is I say that the learning process actually takes place partly during developmental time after the baby is born, but it also takes place partly over evolutionary time during the life of the species. And so the individual baby acquires that. In fact, there are clearly documented and well-studied kinds of learning that take place during fetal development. As a matter of fact, Jim Bednar is the person whose I was on his thesis committee, and where I first encountered that. There's a bunch of things about the visual cortex, and doubtless other parts of the brain, that are learned. That is, they're not wired in, they're not genetically specified. They are learned during fetal development. That while your visual cortex is developing, there are genetically specified stimulus generators that effectively work like a screensaver that run over your retina and provide artificial stimuli, and then the nerves of your visual cortex learn some of the basic information for visual processing from that process. And so, all learning curves are exponential. So the thing about exponentials is that they have this long, long flat part. And so if you can get up that long, long flat part before you open your eyes, that's a huge help for learning how to deal with your visual cortex. So in fact, a lot of learning takes place over evolutionary time. But as a research strategy, I pretend that it's all done by the individual. And as the animal examples that you cited demonstrate, the boundary between evolutionary and individual learning is different for different species. So humans take a long time to learn to walk. Antelopes do not. And there's excellent evolutionary reasons for that. I might have time for one more. Yeah.
Yes, thank you very much for your talk. I would like to ask about time, the time consideration in semantic maps.
Yeah.
Because for robots, maps are usually done considering a fixed environment, but the reality is that the world has a dynamic.
Yes. Okay, that's a very good question. I mean, how do we deal with dynamic aspects of the environment? And fortunately, I've got several slides that are coming up after the break that will address exactly that question. Thank you. All right, so let's have some. Did you have a question? Why don't we actually go get a cup of coffee now, and then we can. Okay, go ahead.
There are kinds of spatial learning that are distributed over a community.
Right.
And maybe you're going to mention that. But the very interesting case is ants that teach other ants.
Yes. Okay. That's fascinating stuff, and in fact, I don't address that. So it's really interesting, and it would be good to. Somebody should look at that, like you. Okay. Thank you. Okay, well, thank you very much. So now we move on to chapter 2 of this, which I call bootstrap learning, because somehow we have to be able to pull ourselves up by our bootstraps. And so one of the questions that I ask is where does semantics come from? How do you get meaning, particularly if all you've got to start with are pixels? I introduced this in the beginning of the basic SSH when showing how we got places from the behavior of systems in control. And I'll actually go through that point briefly in this talk as well. But then we'll go on and do a bunch of other stuff. And as before, there should be plenty of time for questions. So feel free to raise questions as they come up, and we'll go on. All right. Now, people do AI for a whole variety of reasons. And probably the most common reason is to build smart machines. And so that raises questions like, what does a robot need to know in order to be useful? And how do we find that knowledge and use it for robots? How do we build robots, Another problem is really the cognitive science problem, which is, what is mind? How is it possible for a physical object to have a mind? Which is really one of the great foundational scientific questions. And that leads you to what kind of knowledge is foundational to having a mind. Now, I often feel that there are sort of half a dozen or a dozen really big scientific questions. Like, I mean, what is the universe and where does it come from? What is life? And where does that come from? What is matter and energy and so forth? And this question of what is mind is one of those big questions. And one of the privileges that we have in working in artificial intelligence at this particular time in history is that we have the opportunity to work on one of these really, really big questions at a time when we have acquired methods that provide new leverage on that. And so for the past 60 years or so, we've been able to work on a set of questions that were really impossible to work on before that. And I make a metaphor with the early history of physics, that before people like Newton and Leibniz developed differential equations, you did physics primarily in natural language. You would write insightful essays. You could, in fact, write algebraic equations too. But there were questions and hypotheses that were impossible to state. And so once you had the language of differential equations, you could state things that you weren't able to state before. And some of those things would be true and some of those things would be false, but you had a language for stating them and you had methods for deriving consequences from those hypotheses, which you could then go out and test. And I feel like in a lot of ways, computational methods in AI play the same role, starting with symbolic methods and at the birth of AI, but also neural methods, statistical methods, a variety of other things that have been developed since then, give us a much greater ability to state things, to state hypotheses about how the mind works. And again, some of those are right, some of those are true, and some of those are false. But science isn't scared of false hypotheses. Far from it. I mean, that being able to clearly state and test false hypotheses is how science makes progress. And so if you read the history of science and you sometimes think, wouldn't it have been amazing to have been alive and working when people like Max Planck was doing his work and Einstein was doing his work and people like that were doing all of these amazing, unbelievable things? Yes, it would. But that's actually where we are in AI. And so I feel like we're immensely privileged to be able to participate in this. And so we should savor every bit of it. But also, it's a centuries-long problem. And so some people get discouraged because it's been 60 some odd years since the Dartmouth conference, and we haven't solved the problem. Well, I'll actually say a little more about that in a moment. I started graduate school just shortly after Terry Winograd finished his thesis, and he built this program called Sherdlu. How many of you are familiar with Sherdlu? 1, 2, 3, 4. The rest of you are illiterate. So Sherdlu was a wonderful system that it lived in a world that consisted of blocks on a tabletop, and it had an arm, and it could understand natural language, except of course it didn't have a tabletop of blocks. It actually had a simulated tabletop of blocks. So its world, it did have a world that it perceived and could act in. It's just that its perceptions were not physical perceptions and its actions were not physical actions. But that really didn't matter to it, and it shouldn't matter to us in a lot of ways. Although it does mean that they didn't have to solve some of the harder problems of perception, but they did still have to deal with it. The focus of Terry Winograd's work was on the natural language understanding, but also the planning and acting. It was able to do very impressive conversational interaction, and it would do things in its world in response to that. And it would be able to explain why it did things. We were just so amazed that we knew that a huge step forward had been taken in artificial intelligence. We were going to solve this problem in 5 years, 10 years max. Well, it didn't happen. And so one of the real questions is why? So my claim is that a really important part of that is that Sherdlu knew a bunch of impressive things, but there were a lot of things it didn't know. And so it didn't know what a block is. It didn't actually know what objects are. I mean, it had data structures that represented objects, and it didn't really know what actions are, although it knew that it could invoke an action and it would result in a procedure being called that would make a transformation in a data structure. Really had very little notion of what places are or what properties are. They were just sort of labels. So there were things about the world that had been kind of glossed over here. And the problem of solving those and figuring out how both to represent that knowledge and how to acquire that knowledge has turned out to be a lot harder than we originally thought. So the conclusion, among the conclusions from that, is that we need to learn those kinds of foundational knowledge. And that the kind of symbolic representation and inference methods that are sometimes called GOFI, good old-fashioned AI, that was a phrase that was made up as a derisive phrase by the philosopher John Hoagland. But in fact, I think it's a perfectly good word to refer to some very, very powerful methods. They're very powerful and very useful and not sufficient. But lots of things are not sufficient. And so we clearly need a bunch of other things that people are exploring a lot of them now. And so we get probability theory, machine learning, control theory, dynamical systems, and so forth. Now, I think all of us who have been around for a while have gotten very familiar with the notion that people get all excited about a particular idea and say, this is the solution to all the world's problems. And then it turns out sometime later we discover that it's not. And then everybody gets all excited by this idea and they say, well, that's the solution to all the world's problems. Well, it turns out it's not either. And then, well, maybe it's this and this. Or maybe it's this and this. Well, that's not it either. So I think the whole notion, one of the reasons why I emphasize the semantic hierarchy idea is that solving all the world's problems requires a lot of different representations. And so there is no single silver bullet here. We're going to have to use a number of methods. And part of the challenge is how to use these different methods and these different representations together. Another thing is that these foundational domains of knowledge, and I'll make a list later, need to be learned by an agent that is embodied and embedded in its world. So it has to have sensors and effectors and ways to interact with its world so that it can learn things from that. We're certainly not going to be able to program this up by hand, although it's an understandable shortcut at an early stage of a difficult field. Now, John Searle is a distinguished philosopher who is an adamant opponent of AI, and so has his head seriously wedged in certain ways. But he made a dramatic argument against the possibility of computational models of mind. And he's got this fairly dramatic Chinese room argument, which I'm not going to talk about right now. But the fundamental essence of his idea is to say that, very reasonably, that the knowledge of an intelligent agent has meaning. It refers to objects in the physical world. That seems very plausible, right? That I look at you sitting in the audience and I say, that's you. And you're sitting on chairs, and that knowledge is referring to the chairs, and so forth and so forth. Computation, as such, is a syntactic, meaning-free manipulation of symbol structures. Symbols can refer to things. Tarski has a nice theory of semantics and truth, but they only can refer to other symbols. So, intelligence requires meaning, computation is meaning-free, therefore, the mind can't be explained by computation. Boom. End of story as far as John Searle is concerned. Now, people have been sort of wiggling on the hook for a long time, and I'm gonna postpone talking to Aaron about this because we could spend arbitrarily long.
He says it cannot be explained, but it can be simulated in as much detail as we want.
Yeah, but
That you haven't replicated. That's the only point I want.
okay. Now, I think that actually this argument has a certain amount of genuine weight. Now, he claims that it refutes the possibility of AI, and I think he's just wrong. But I think it tells us something, and it directs our attention at an interesting question. And so there's been a bunch of replies, and so I'm wanting to state what I will call the constructivist agent reply, which says, okay, fine, you are right, John. Of course, John doesn't pay any attention to this. But both in robots and also in humans, knowledge does not refer in the logical sense to objects in the external world, because objects in the external world are not the kinds of things that Tarskian reference can apply to. As a matter of fact, even having objects in the external world is kind of begging an important question, because you don't have access to that. You have access to pixels. And that's what we're going to get to. So what the agent ends up doing is constructing its own internal knowledge structures that track and explain certain patterns of interaction on its sensory interfaces. And that those constructed knowledge structures are the kind of symbolic things that logical reference can refer to. Now, so in effect, we're creating hallucinations inside our head that track the sensory signals that come in, and then we refer to those. But if we can just construct essentially arbitrary hallucinations, they could be arbitrarily far out of correspondence with the world. So that doesn't seem to make much sense. On the other hand, if my model of the world is arbitrarily far out of correspondence with the world, I'm going to get run over by a bus, which is a little bit of a joke, but in fact, it's actually a critical thing. That is, evolution takes care of creatures whose model of the world is sufficiently far out of correspondence with the actual world. That you need to have a useful model to survive. And so our task is to figure out how to make this actually work. Now, many years ago, William James wrote one of my favorite quotes, which modern developmental psychologists say is absurd, but I still think it captures something interesting. The baby, assailed by eyes, ears, nose, skin, and entrails at once, feels it all as one great blooming, buzzing confusion. Now, the baby probably doesn't do that. On the other hand, I say that there's nobody who understands blooming, buzzing confusion like a roboticist. Because blooming, buzzing confusion is what's coming down the wire. And you really have to figure out what's going on there. And so that's what we get to do as we build these models. Now, one thing that's important is I'm going to pretend that our robot baby, or what I'll often refer to as a learning agent, is learning all of this during its developmental time. As I mentioned earlier, in reality, some of that knowledge is actually learned over evolutionary time and is built in. And some of it might be learned during fetal development as guided by evolution. But we're just going to pretend that it's learned by the individual and focus on how the ontology enriches, how we get a better model of the world. So, I made this agenda. This is a little bit of a post hoc agenda to sort of describe the path that I hope to follow. Oops, let's see here. We've only gotten part of the way along it. If we have the learning agent that I spoke of that has an uninterpreted sense vector, uninterpreted motor vector, and needs to learn about its sensory motor interaction and about the things in the world. About the things in the world, then it's first going to have to learn about its body. Sensory input, motor output, needs to learn control laws to do various things. It needs to learn about the structure of local space and then large-scale space. It eventually needs to learn about objects and actions and relevant properties, affordances, eventually tool use. The agent needs to learn to make plans, and plans exist in order to achieve goals, and they are made within the context of the agent's beliefs about the world. Now, all of this stuff can be done by essentially a solipsistic agent that just interacts with itself. But once we have goals, beliefs, and plans, we start to have the machinery to be able to comprehend other agents and to be able to say, well, other agents might have goals and beliefs and make plans too. And so I'll just kind of brush on that, and once we believe there might be other agents with their own beliefs and goals, we can start thinking about problems of communication. Now, I believe that we'll talk today about getting about halfway through here. And these are future things, but I'll say a few words. Yes?
So unlike the other things on that list, goals and beliefs are not external
Right.
to the agent.
Right.
So from the point of view of learning, I cannot just observe what's going on and find some patterns.
Right.
And also, if it wasn't for goals and beliefs, I wouldn't be doing all the rest. So there's no reason to learn anything else if there's no motivation.
Right.
So how is that? Is it the same process or is it different?
Well, in some ways, yes. So I think in a lot of ways it's the same, because you have a certain number of goals and motivations that are built in. And it's actually fairly controversial what those are, but there are drives that you need to satisfy. And one performs actions that help achieve some of those goals. As you start doing certain kinds of internal processing, some properties of that internal processing sequence become observable. So they do actually become things you can observe, even though they're just going on inside your head. So I think that regularities and structures there are also learnable. Now, I'm getting very hypothetical here because we haven't actually done that. But I will say a few words on a slide at the end. Now, I'm gonna actually go through in the usual detail some slides you've seen before, because I think it's worth, they were at the beginning of the previous talk. But this whole idea of learning higher level concepts from lower level inputs without sort of cheating and telling it what higher level concepts it wants was sort of inspired by the notion of learning places from the notion of distinctive states. So we realized in the course of doing the cognitive mapping that we could learn high-level concepts like places and paths by abstracting the behavior of low-level control laws, which are taking place entirely at the pixel level. And so here are various references. These two were on the previous set of references, but actually the first work here was with my student Jung-Tai Byun, published and this is a journal publication in '91. There was a AAAI paper in '88 that did this stuff. So, and so here again is this notion of a distinctive state. So I can define control laws even without knowing, for example, that my sensors are telling me the distance to the wall. I can just know that there is a feature, and that feature, if I move in a certain way, I can keep that feature close to a certain set point. So I can travel along here maintaining that feature close to a set point and making progress with respect to some other feature without even knowing what that feature is measuring. And then hill climbing can take me up to the local maximum of some feature. And I have this pattern of behavior. And if I can do trajectory following and hill climbing, and then return by doing trajectory following and hill climbing, then I can abstract that pattern into this much more concise pair of places and the link between them. So, and as Alan was pointing out earlier, it's actually, it's vulnerable if the errors are big enough that you miss the basin of attraction entirely, then the abstraction fails. But if you can keep those within bounds, then we can get this abstraction. And so we demonstrate that you can travel through and explore a previously unknown neighborhood. And notice that the robot is really only following sort of a small subset of the entire neighborhood. It's building a lower dimensional manifold within this infinite size space. And that allows us to abstract it to this graph. And so this is kind of an example of building higher level concepts from lower level experience and looking for very particular kinds of regularities in them. So we started to explore this, and I often think of it as we've got this huge, deep canyon needing to go from pixel level experience to high level concepts. And we built a simulated robot, and a lot of things were inadequate and limited and not the way you would really like it to be in the end. So I think of it as a fragile, rickety bridge across this huge, deep canyon. And every part of that bridge was a hack in some sense, perhaps, and could and should be improved, but it actually got all the way across to the other side. And so that's part of what you need in order to go on and replace the fragile, rickety bridge with a big, solid, well-engineered one. And so our goal here is to go from pixel level sensors and effectors with no higher level semantics up to space, objects, actions, goals, and plans. That's our job. Well, that's a big agenda. So we're going to do it in a very particular setting. And so this is a robot called Lassie. Lassie is a Magellan robot built by iRobot. They've stopped building laboratory robots, I'm afraid. This is a SICK laser rangefinder. This is one image from the SICK laser rangefinder showing the distances to various objects. This one measured 180 ranges over a 180-degree planar field of view. That plane was about 13 inches above the ground, and it scanned about 10 times a second. So it's much simpler than vision, and it's much more easily understood. But I think it illustrates the essential properties that we want. Now, we're actually going to make this even harder. So the hardware of the SICK laser rangefinder actually knows that the distances and directions of the laser scans are what they are, as shown here. But we're going to assume that it's more like the optic nerve, which goes centimeters and centimeters way to the back of the head, and we're just going to treat it as a big cable with a bunch of signals, and we don't even know which fibers are attached to which receptive fields. So the sensors are all scrambled up. So we're going to state the problem as given a disorganized and uninterpreted set of pixel level sensors, how do you make sense of it? Now, there are several other problems that my my student and I worked on, and if you see the paper in the AI journal, it'll talk about that in detail in his thesis, but we won't talk about that in this talk. So this is what a 180 pixel disorganized range sensor looks like. So this is a clip of experience. These are all scrambled up. This is what is happening in the world. So what is going on here? What can you do? That's horrible. Something is happening, and you don't know what it is. So what can we do with that data? Well, what we've got is a 180 element vector. So one of the things we can do is we can compute correlations between every element and every other element of that vector and find out which ones are correlated. And if we do that, we can treat that correlation as a distance metric, saying high correlation means it's very close, and do a kind of multidimensional scaling. And I'll tell you the details later on. And that does allow us to recover the correct sequence of those sensors. And so the result, this is the same data. It looks like this. And as you can see, it's significantly more comprehensible. One of the things that's worth knowing is, let's see if we can get the legs again. Yeah, there's a pair of legs here. I think sometimes you can see the separation between them. This is a wall. That's what a wall looks like with the transformation here. That's the edge of some object. Now, in fact, the method that recovers the structure of the sensor also places them in a 2D space. Again, I'll explain that, but it allows us to get this kind of view of the world, which we can actually recognize as an egocentric range image. So the origin is right here, The egocentric origin is right there, and its view of the world is sort of turns around the origin. And some of the changes that the robot observes come from its own motion in the world, and some of it comes from the fact that things are changing in the world. And it really doesn't know very much about how to distinguish between those. And I believe that this is where I pause to explain how it's actually done. Right. So, what we want to do is to estimate the sensor similarities, starting with a completely disorganized bag of pixels. So what we're going to do is we're going to compute a distance metric that will tell us a distance between every pair of pixels, Si and Sj. And so we're going to look at the time points over some fairly long interval, and we're going to take the absolute difference in the values of those sensors at each time point and take the average of that. This is essentially L1 distance, what's called L1 distance in a certain corner of the world. Euclidean distance is called L2 distance. You would square this and take the square root of the result. And that metric is actually the heart of a very influential dimensionality reduction method called isomap. Another researcher used mutual information. One of my students used Gaussian processes for this purpose. It's not really critical to my mind exactly which distance metric you use, but the fact that there is a distance metric that can be applied to pixel level information and give you a distance, a pairwise distance on these pixels is the important part. And that none of these metrics involve knowing the semantics of the sensors. So now, once I have this distance metric, I can take the sensors that I have. So this is k plus 1 sensors, and I can embed them in a higher dimensional space, Rk, according to those distances. So I basically get a k-dimensional point cloud. And now I can use principal component analysis to find the dominant eigenvectors, which is to say I want to figure out the shape of this point cloud. And in particular, what I'm looking for, and what turns out to be the case, is that this point cloud is actually a pancake, extended in 2 dimensions and very thin in the others. So that's demonstrated here, that shows the eigenvalues. And so the first 2 eigenvalues are high, indicating that there's a lot of information in them, and the remaining ones are very small. So once I've identified this 2-dimensional space within that Rk, I can now take my sensors and project them into that 2-dimensional space. Now, for this particular example, what I had was a simulated robot with 24 range sensors, but just for fun, I assumed that one of them was broken and gave a constant value. And so what we would do is then take that point cloud and project it into the 2-dimensional space defined by those 2 eigenvectors, and that was able to reconstruct a really good picture. Now the algorithm also then says, starting with this, what we'll do is use a relaxation algorithm to adjust those positions to use all of the information in the distance metrics. In this particular case, since there's so little information left over, you actually can't see a noticeable change. There are noticeable changes, but it's hard to find them. We'll see another example that'll give something better. We also applied the same method to real data from the laser rangefinder, and it found this structure for those sensor rays. We also decided to try it on something that wasn't so ring-shaped. So we defined the roving eye as a low-resolution rectangular retina that would move around this photograph. And in this case, our eigenvalues, the top two were much higher than the others, but as you can see, there's an awful lot more juice left over in the upper eigenvectors. So the projection of those 25 sensors is this, but taking this as an initial state and then relaxing it using all the information gives us this rectangular grid. So it's essentially allowing the robot to recover the anatomical structure. Notice the robot hasn't been given any knowledge about the structure of its own body or of its own sensors, but it can recover the structure of its sensor arrays from the properties of the sensory images. So we've already got something pretty striking. So here is, I'm sorry about that. Whoop. That's what I get for, uh-oh. Now I'm in trouble. All right, sorry about that. All right, here's the egocentric range. And so this is, as we've seen, this depends on us having recovered that semicircular arrangement of the lasers. Depends on us having recovered the semicircular arrangement of the lasers. Now, take a look at this. So here what we have is a wall. You saw the feet of some person walking away. There's clearly some things that are invariant for a period of time and other things that change. Now, disentangling those invariances is a bit of a trick. So we apply another method which depends on something called a method called iterative closest point that says the egocentric observations are a sequence of frames of range images that at closely spaced points in time. And now what we're going to do is we're going to take the first frame and declare its frame of reference to be special. And then we'll take the second frame, which shifts a little bit as we see that's what happens with an egocentric image, and we're going to shift it, we're going to translate and rotate slightly in order to maximize the match between the two frames. And then we're going to take the third frame and shift and rotate to maximize the match with the other two, and so on and so on. Now what this does is it gives us the same thing, but all within a single frame of reference. It's actually the frame of reference of the first frame, but what we would call a world-centered or allocentric frame of reference. And one of the things that's very interesting about this is that now the egocentric origin, which used to be fixed at the bottom, now has a trajectory. It has a position and an orientation that change in time, so it has a trajectory through the world. So we've added something new to the representation. And what that something is a representation of where the robot is, of the robot's own egocentric point of view. And so, I mean, notice this. This is actually a fairly peculiar thing that we've done with the ontology. The sensors never sense the robot's body itself. They only sense the external world. Nonetheless, we've been able to create a symbolic representation for the robot's body, for the robot's point of view. Did you have a question? You know, you're just waving your hand around. Okay. Now, when I first started creating this display, I really liked the notion of, excuse me, using red dots for the data and having a blue line connecting each red dot to the origin or the x-axis, respectively. But at this point, the blue lines are getting to be a nuisance. And so, this is the same data as this last frame, it's just without the blue lines. And as you'll see, your visual system is able to get a lot more information out of it, seeing what's going on there. So that's, so you can see there's more going on. It's still actually a little bit hard to make sense of because it's so much in the moment. It's not showing you much about the history. So one of the things that we can do at that point is to say, we now have this world-centered frame of reference, this two-dimensional world-centered frame of reference. We can divide each of these dimensions up into a fairly fine-grained set of bins to create a two-dimensional histogram, which is to say a grid. And just count how often observations land in the various buckets of the grid. If we use a little more information about the, the rays, we can actually use evidence that a particular bin is empty. And so what that amounts to is the occupancy grid representation. And so what in this representation, this is that egocentric origin. The red is what's visible at in the current moment. The black represents the static parts of the world, the things that it has observed over a significant period of time. The white or light blue represent cells that are empty because it's looked through them. And so what it's effectively doing here is building a static world model of the world. So now we have to pause a little more and see how we write that down more formally. What we've got, the observational data that the learning agent has is this sensory stream. Now, this is enormously high dimensional. So it's 180, it's 180 sense elements by 10 times a second for however many seconds you have. And the movies are not, the movies are a short selection of the actual experience of the robot. And in the course of this, what the occupancy grid representation is doing is teaching us a static model of the world. That is, it's still got quite a lot of information, but it doesn't change with time. So it's got, I mean, a bunch of cells by a bunch of cells. And it's also, we've also learned the trajectory of the egocentric origin. Now the trajectory has a lot of time points, 10 times a second times the number of seconds we've got, but it's only got 3 dimensions, x, y, theta. So we've taken this fairly huge amount of data and we factored it down into a static world model and a trajectory. And then we can define a fairly simple projection function that says, given that model and a point of view, what should I be perceiving? And the theory basically says this is going to explain a lot of that. But of course, it's not a perfect explanation, so there's some amount of noise left over. And so what we're doing is essentially compressing the information in the sensor stream in terms of the static world and the observation pose. And what we're going to be doing is we're going to focus a lot of attention now on that error term, which is the difference between this prediction and what the actual observation is. So, now we've used a bunch of methods in here. Just like not using one representation, I don't like to use just one method, and so I've referred explicitly to many of these and some of the others implicitly, but there's more. Basically, the theory is, or the sort of working strategy is, I want to say that the sensory stream, the sensory motor interaction is uninterpreted. And I'm willing to assume that the learning agent can use arbitrarily complex or arbitrarily many statistical learning methods, statistical methods to extract the structure of that. But I don't want those methods to encode the answer. So I want it to pull the answer out. Then once this is all done, a next step would be to go back and minimize the toolkit of statistical methods. But at this point in the research, there doesn't seem to be any value in minimizing that. Some people like to start with minimal sets of processing methods, but I don't. Now, our earlier goal was to say we want to learn about space, objects, and actions. And we've learned fairly convincingly about a bunch of aspects of space, but we haven't learned about objects or actions yet. So let's go on to objects. So here's our explanation in terms of the static world. But we've got this epsilon term, which are the discrepancies between this static world explanation and what we've actually experienced. So I'm going to call these the noise pixels. And what we're going to do is we're going to cluster those in space and then track them over time and interpret those clusters as objects. And then, I'm not going to talk about it, but we can then make shape models and we can do a bunch of other things with them. This is work with my student Joseph Modiel, who now works for DeepMind in London, I believe. So here's the occupancy grid model again. The green pixels are those noise pixels. So those are the current observations that are not explained by the black and white static world model. So effectively, a pixel gets designated to be one of those discrepancy pixels, those noise pixels, in case we observe an obstacle in a cell that has had enough previous evidence to let you say with high confidence that it's empty. So we can extract out these noise pixels. Now, as you can see, some of them we can see are probably associated with some object. Others have to do with just noise or errors in the localization. So what we're going to do at this point is, this is the same data yet again. This shows the clustering into objects. They're flickering in color to demonstrate that the clustering is taking place independently at each time point. And we're now using this symbol to represent the position and orientation of the robot, which is at x sub t, the egocentric origin. So then we take those clusters and we match them over time to try to track objects. Now the trackers, so let's watch this one, they go for a while and then they disappear. So it depends on always being able to find a unique successor to any given cluster at one time point. You want a unique successor at the next. So if it splits so there's multiple successors, or if it vanishes so there's no successors, then that tracker just dies. And so what we've done is we've tracked things. The overall result, yes?
So I'm trying to understand why the discrepancies in terms of objects. So what my hypothesis is that they're moving within a static
Yes.
scene, and so that's why they show up as things you can predict.
Yes.
So one of those is pretty static.
Yes.
It's moving anyway. So why isn't that just part of the original static scene?
Right. If the video clip that you see here were the only video clip, then it would have been part of the static scene. So this takes place as part of a longer sequence. And so it got moved in, so it was seen as an object. And you're absolutely right that motion is the cue that tells the learning agent that this is an object. So, and it turns out that does correspond to developmental psychology, because the first cue that babies have that something is an object is motion. Now,
The static model changed over longer time scale, so if I get a new filing cabinet,
yes.
that's going to be part of my static model.
Yes, right. Well, another thing though is like the chairs are pretty much static. So if I have a static world model that includes the chairs, and then perhaps I move this chair. Now, since I've moved it into space that was previously unoccupied, it becomes an object. And I cluster it, it becomes an object. I can characterize its structure. And so I say, okay, that's an object. And now I look at my static model and I say, you know, there's a piece of the static model that looks a heck of a lot like this one. So you never know, maybe it's another one of those, whatever that is. And so if I wanted to check, I can come and say, oh, can I move it? Yes, I can actually. It moves and it individuates in the same way. Because as part of the static world, this row of chairs is just a row of static stuff. Also notice, one of the things that means is that the wall of the room is not an object. Now, as a grown-up, you say, well, of course it's an object. I mean, I can come in and move it. It looks like the sort of thing that workmen can take away if they want to. And even if we were talking about something like that, if I had a big sledgehammer, I could make it go away. But from the point of view of a learning agent, the thing that's learnable is the distinction between the static world and the non-static world. And then within the non-static world, what we're doing is we're pulling out the parts that can be clustered and tracked over time. And those are the ones we call objects. So notice what we've done. Remember, we started out with an agent that had an uninterpreted sense vector and an uninterpreted motor vector. And we moved through this and described the world in terms of the static world, the robot's own pose, an object in a fixed position, but that's actually because it was moving previously, an object with a trajectory. The advantage of the object in a fixed position is that you can then travel around it and gather views of it from a variety of directions, which can then be merged to make a shape model, which I'm not talking about here. We're making observations of individual objects, which we can then match into categories of very similar objects, so as I sort of suggested with the chairs. Now, that's pretty satisfying. But we still haven't done actions. So, one of the things we've learned is object attributes. So, an object has at any point a position and orientation, but we've also said we can learn a shape for it, which allows us to detect changes in position and orientation. Now, of course, if an object is cylindrical or symmetrical in ways, there might be changes of the object that we can't detect. But for our purposes, we're going to assume that we can. And we have all of those things in both an egocentric and in allocentric frames. So now what we're going to do is random movements, which is sometimes called motor babbling. And we're going to record all of the interactions and all of the things that happen. And in that, we're going to search for more clusters, looking for combinations of qualitative changes of some attribute. So if, well, we'll see examples in a moment. So if I can move an object, then it changes its position in the world-centered frame. When I turn, every object changes its position in the egocentric frame, but not in the world-centered frame. Once we identify particular changes of attribute, we can identify the prerequisites of that change, the bounds, putting bounds on the previous states that are consistent. Are there regularities in the bounds on previous states that are consistent with that particular effect? And then when we can, is there a motor signal that makes that action happen? So when we find those clusters that correspond with each other, we define an action as a triple prerequisite, motor, and effect, and this is essentially the STRIPS representation for an action. STRIPS is probably the first major planning system and its representation for actions has been very influential. Now for our mobile robot, Lassie, there really are only 3 learnable actions. And so one of them is to turn, to face something. Another is to move. The robot can move itself within the environment. And another is to push. When it's adjacent to an object right in front and the robot moves, then the object moves. Now we had to put on some restrictions because we wanted to be really careful not to burn out the motors. So if the robot tried to push a wall, for example, it could burn out its motors. And at this point, that particular robot was out of production, and so we would have been in a lot of trouble. So we actually did learn this set of actions. So now we wanted to demonstrate what the robot could do. And so what we did was we gave it a goal location for a specified object. So we simply put that into its brain through brain surgery. And we also gave it a very simple back-chaining planner. If this is what you want to accomplish, this is how you have to get there, and so forth. So that's all straightforward. It would have been lovely to learn those, but this whole project had taken quite a while and my student was getting older, so it seemed only fair to let him finish his PhD. So, this is the demonstration. So here's Lassie, and Lassie is here in the map. This is a recycle bin, and that's this in the map. And this is a goal location, which is a piece of paper taped to the carpet, and that's this location in the map. Now, the robot can't actually sense that, but it knows what that location is. And so Lassie has been told that it needs to get the recycle bin from where it is to over here. Now, the backchaining planner is really straightforward. So the only thing that can change the position of some object which is not Lassie itself is a move action. And so if I have a move action and a desired result of the move, then it knows that Lassie has to be adjacent to the object and on the far side, pointing towards the destination it wants to get to. I'm sorry, it's a push action that does this. I think I said move. But Lassie is over here and it needs to be over there, so by backchaining some more, it needs to get itself over there and then turn to face the correct direction. And in order to do that move, it needs to rotate, means to turn in order to face where it needs to go. Yes?
Something subtle that you skipped, I think.
Okay.
The robot has formed these representations
Yes.
of the scene and the object scene.
Yes.
So there is internal representation, not one that you specify.
That's correct.
You now want to specify actions on the objects that it's learned about. So it somehow has to communicate to you, this is what I call this object, this is what I call this place in the scene and so on, so that you can have that communication. It's not quite clear.
No, that's actually it. It has also learned the actions.
Yeah.
And it has learned which objects it can apply those actions to. Now so turn and move apply only to the robot itself. But push applies to movable objects. So, and now in that scene, there's only one movable object, which is the recycle container. But in general, there were two or three.
But you're supposed to be able to tell you, these are the objects I've learned.
Yes.
This is what I call them.
That's right.
But the point is, the desired point is a bit more subtle still, because it won't have a name at that point.
That's correct. And so when I said here, so those are important research issues that we have glossed over. So we have not actually addressed those particular things. So we do brain surgery to get that in. So we can examine its internal data structures. This is one of the benefits of developmental robotics as distinct from developmental psychology, because you can open up your subject and you can examine its data structures, and then you can reach in and put those things in. So we gave it a goal location and we said that this was for that object. And we're able to say that because we can examine its internal data structures, which obviously you can't do with other people. So yes, the coordinates of that point expressed in its axes of representation, I mean, we had to do that by hand. So it makes the plan, and then we're going to carry it out. So Lassie turns, heads up there to get adjacent to the recycle container, turns to face in the correct direction, contemplates something or another for some period of time, pushes the recycle container over to the target, and it misses. So it thinks a little more, it gets around to the other side, it turns in the correct direction, and it nudges it into place. Woohoo! So you get all excited about driving a car, a self-driving car over 150 miles of Nevada desert. This is the real thing. None of this desert driving or driving through Palo Alto or stuff like that. I mean, so this is an example of a constructivist agent. So it constructs its own models of itself and its world, its own sensors and motor controls. It builds these egocentric and world-centered spatial frames. It learns about objects, shapes, and localization. It learns about actions and their properties. And it can paste these things together. And the interesting thing is that these are self-created abstractions. These are not provided by an external authority. So doing this through a process of intelligent design and simply programming it up would be an elementary exercise for a robotics student. But actually having the agent experience the world and build its own model of the world and then do it, I believe, is a step. Now again, I mean, to be honest, this is another one of these sort of rickety old bridges that, I mean, there's a bunch of places where this argument really needs to be firmed up and tightened and generalized and applied to more examples. But the fact is we got to the other side. And I think, I mean, it also demonstrates that although these actions are self-created, they're self-created on the basis of a fair amount of sensor information from the world. And so, in fact, they correspond adequately well with the actual properties of the world so that they can guide genuinely effective action. And so I think this is a recipe for doing much more in the way of robot learning. So we go back to our bootstrap learning agenda, and I believe that we have demonstrated how to learn the sensors and the motor commands, that part I didn't show you, and the control laws, how to learn a spatial model, how to learn about objects and actions. Now, there's a lot more to be said about goals, beliefs, and plans. We really just programmed that up and stuck it in. And eventually it would be awfully good to learn about other agents. So I feel like we're making progress. Another 50 or 60 years and we'll probably have something really impressive to show. Yeah?
So my question is put into sharp focus by the last one of those.
Yes.
If you want two agents to each learn essentially knowledge of the world and then communicate and
yes.
collaborate on a joint task,
yeah.
This problem of communicating their world models.
Yes, right.
And that I think that would be a very interesting challenge to understand
yes.
how they can come about with the shared semantics, because they may well have subtle differences.
So in principle, they could, their individual semantics could be arbitrarily divergent. Now, the needs of communication impose some pressure for aligning their semantics. Now, alignment of semantics is also a major theme that's being addressed by a number of people during these tutorials. The thing I would like to really point out to is the work of Luke Steels and his associates and students, where they've actually had robots that would arbitrarily invent lexical tokens, words for things. Okay, all right. So, okay. Any of Luke's students in the room? Okay. They're probably next door. Yeah, right. So this process of getting your representations into alignment can also be addressed within this kind of framework, and I think Luke's work, and I mean, it's not only Luke who does this stuff, but that line of work is really very important here. And of course, I think we also have to recognize that we don't get our concepts all that much into alignment. So when we talk about certain very physically grounded concepts like chair or floor, then we get our concepts pretty well aligned. But if I talk about concepts like patriotism, now what does that mean? Well, that means very different things to different people. If I talk about representation, I mean, I could have a long conversation with an AI colleague and we're bandying about the word representation or abstraction, and we may have no idea what the other person is talking about. So actually grounding those and aligning those is a real trick. One of the things I wanted to spend a little bit of time on, since I've only got a little time, is moving on from there. And so I won't spend much time on this, but we did decide to go on from mobile robots with lasers, which basically means they live in a 2D world, to a humanoid robot with eyes, arms, and hands. And so this led to some work with my student Shanghai Xu, which we call the object semantic hierarchy, which is another hierarchy of representations about objects, building up from 2D to 2D surfaces in 3D to 3D objects and so forth. Progressively explaining the properties of 3D objects in the world from visual observations, not just laser observations. And we did with a simulated robot, my student Jonathan Mugen and I developed a more complex and sophisticated model of actions and action learning, and tested that with this simulated robot that had one arm and a tabletop of blocks. It's a little more dexterous than Sherdlu, but not a huge amount more. Now, as I promised, we can think just a little bit about the theory of mind. And so what do we know about other agents, and particularly goals, beliefs, plans? Objects in the world, one of the first things that children learn is whether an object is animate or inanimate. Now, children early on think that cars are animate, so because they're self-moving. And they may think that plants are inanimate, for example, and arguably they are, but even though they're living. And so one of the early distinctions is, how do you predict or explain the behavior of an object? Now, for an inanimate object, there are versions of Newton's law, or probably more realistically, more cognitively realistically, Aristotle's laws, for predicting the behavior of inanimate objects. And so, if you know the forces on an object, you can infer how it's going to move. And likewise, if you observe an object moving, you can draw inferences about the forces on the object. And so it's pretty straightforward. And depending on exactly what your theory is, you see an object moving, you can predict its future. With an animate object, an agent, well, if you know the agent's goals and beliefs, then you can infer the actions that it will take. You might be right, you might be wrong, but you're a lot more likely to be right than picking something randomly. So an agent is likely to select an action that helps it reach its goals in the context of the world that as it believes it to be. And conversely, if you see it acting, you can infer its goals and beliefs. So if I see you sticking your hand in the cookie jar, I can infer, you know, you probably want a cookie. And then, if I have inferred that you want a cookie, then I know a goal, and then I can say, so if if you find no cookies in the cookie jar, but then you look around, I can see, for example, that there are cookies on the plate, and I have inferred that you want a cookie because you went to the cookie jar, then I can infer that the next thing you're likely to do is to look around and then take the cookie on the plate. Now, developmental psychologists are very clever at setting up experimental settings where people, young people, have various kinds of beliefs, some of them true, some of them false, and they perform actions in accordance with those, and maybe other young people are observing the situation and making predictions about how that person will behave. And so this is generally called the theory of mind, and there's a substantial and very interesting literature about the developing child's theory of mind. And part of just dealing with the world is developing a theory of mind for other agents. And so that's, I mean, we spent some time reading and speculating about that, but we haven't done any implementation work. And so this sort of touches on another round of things, which is how does an agent learn to live in a world that contains a lot of other agents? And so the first part of that is what I spoke about before, which is developing a theory of mind so that you can predict the behavior of other agents. Another issue is learning by imitating other agents. So if I observe you doing something and I wish I knew how to do that thing, the question is, how do I practice that? Now, expecting me to record all of your joint positions and replay those joint positions is A, too hard to do, and B, unlikely to succeed. So the approach that we'd like to do is to observe that and infer the state space and the reward to define a reinforcement learning problem. And then I try to solve that reinforcement learning problem with my own capabilities. And then we start having this issue about learning rules or learning morality and ethics for cooperating with other agents, for improving behavior with other agents in order to produce better outcomes for everybody. And one of the things that seems to be an important part of this, along with trust, which I spoke about quite a lot last night, is the notion of punishing free riders. So free riders are people who take advantage of the cooperation of others, but don't actually do their share to contribute. This is one of the big issues that shows up in that world. So, lots of things to do, plenty of things to read about the various steps that we've taken in this direction. But again, I think this is a research direction that is very exciting, very promising. I'd encourage you all to work on it. Thank you. Questions? Yes.
In philosophy, there's a lot of discussion about, well, a priori, if we have some categories for objects or maybe logical capabilities that are given in advance, no? And according to your explanation, if a baby, no, would develop its capabilities that way, so many categories like what is an object or location, spatial, organization of space and all that would be something that is developed on the go, no? So, in a sense, no?
So that's true here.
So it also affects this maybe universal grammar idea in a sense, or?
Yes, it's a very, very interesting question about what needs to be a priori here. And part of this enterprise is to actually to try to restrict the amount of things that need to be a priori. So first, if I make this move of saying I'm going to treat learning over evolutionary time as the same as learning over developmental time. So the prior, I mean, obviously they happen in different ways and there's different algorithms and so forth, but that things that are learned over evolutionary time are not considered a priori. So then where did the prior knowledge come from? What kind of prior knowledge does this picture require? Well, it certainly requires the ability to do a lot of detection of statistical regularities. Well, but actually, and I can see Aaron sort of wrinkling his forehead on this one, but I think that I mean, if I can infer what Aaron would say, and he'll probably tell me right after, that even the detection of statistical regularities can be learned over evolutionary time. That if we can discover various kinds of statistical regularities between types of events, and then develop detectors for those kinds of regularities, which would then be usable in a bootstrapping way for something else. But for this, I mean, I'm claiming that you don't really need, well, let me back this off just slightly. In what sense would knowledge of space be a priori? So this picture says the knowledge of the spatial structure of the sensor, the two-dimensional structure of the sensor, comes out of the two mathematical dimensions that are defined by the principal eigenvectors that come out of this principal component analysis. And the principal component analysis is something that can actually be implemented in a straightforward way on a simple neural network. So if you just take a couple of several neurons, and you take the input and you put them through two neurons, and then you send it back out to the output, and you say, how well does the output match the input? The two hidden neurons are going to end up converging to something that spans those two dimensions of the principal those principal eigenvectors. So there's a mathematical property that will give two spatial dimensions the fact that they get interpreted as spatial in the perceptual world comes out of applying this to the perceptual data. So you don't actually need, I mean, it doesn't need to be a priori, is what that says. It sort of comes out of the mathematics. Okay, anybody else? Yeah.
The robot that you were showing that was pushing the bin, it seems that it learns to behave in that particular environment, right?
Yes.
But if I want this robot to do a similar task in another room with a possibly different object, not terribly different object, it could be able to do it, presumably.
It would.
It could?
Yes.
So, but it would have to learn from scratch. And I was just wondering about generalization. Can you comment a little bit on that?
So let's go back and get this one. So this robot, let's think about what it's learned. Let's see, I think I have, so it's learned the structure of its own sensors and motor controls, right? So that's something that it could carry. Suppose it leaves this room and it goes to another room down the hall. It would certainly carry that knowledge along with it. It learns about egocentric and world-centered spatial frames. Now, that would also carry along with it when it went to the new environment. It learns about the existence of objects, shapes, and localization. Well, that too, the method for learning objects and separating them from the static world through this criterion of identifying the static world, identifying the discrepancies, clustering and tracking them over time, that also would work in the new environment. Now, the new environment would need a new map. So it would have to go into that environment and observe that environment and build a new map of it. And it would have to learn, and it would localize itself within the map, but it would have learned the ability to do that localization. And it would also learn how to identify something as an object if it had seen it moved around, or if, for that matter, if it could push it around. It would recognize that this was an object and that it was pushable. It would learn these actions, and that knowledge would carry forward to the new room. Although I have to say that this is a very good suggestion, and so in fact I think it would be a very exciting thesis for somebody, maybe a master's thesis, but I mean it would be a big master's thesis.
Just a clarification, the actions are not learned. The action selection is learned, but the actions are predefined.
No, not at all. So what happens is it does random movements. The way it learns the actions, it does random movements in the world just doing little motor signals. So just like we're going from pixels to objects, we want to go from motor signals to actions. So a motor signal would be a little tiny twitch of one sort or another, and an action is a consistent, the effect of a control law, for example. And so what we're doing here is lots of motor babbling, recording these interactions, detecting which changes are caused by which signals, given that you were in a certain previous state. And so those actions are actually learned by clustering these things and associating them with each other. We create these things, And it's those clusters that are learned. Now, putting these names on them is a thing that we do. But that's simply giving them comprehensible names so that we can tell what the robot is doing. But so the robot creates action 1, action 2, and action 3. And what the robot knows is that action 1 has its prerequisite, its motor, and its effect. Action 2 has its things. Action 3 has its things. So it actually does learn the actions. And that's an important part of it.
I think that rather clean that it would learn just those actions. I would expect that things would be a bit more noisy and it would learn several different versions of move with slight variations.
Well, you probably have to go back and look at Joseph's thesis to see the various little bits of noise. There are certainly, are little bits of nonsense that appear in these things. But it actually does, it does a pretty good job.
There's no more questions.
Oh, I think Aaron has, yes.
I think it's a wonderful philosophical experiment.
Thank you.
I think it's a wonderful philosophical experiment. I'm assuming you're not claiming this is what evolution actually produced.
That's
no. Right.
Scientific
Sure.
question for someone else.
Right. And at some point you would presumably want to know what's there in humans and what might be possible in future robots to give them the same kind of a benefit of evolutionary learning, or in our case, human learning, so that one could start in a different way. The bootstrapping would then be perhaps much more directed, and there might be quite different intermediate cases. Anyway, one small follow-up question. In your work, or Joseph's, has anything been done about learning about other agents and their internal states?
Well, I guess we focused on this thing, pretending that the evolutionary learning takes place in the individual, basically in order to explicate the dependencies of these various concepts on lower level things without a lot of prior knowledge. So I think as in future research, somebody else should look at what happens if humans with all of their rich knowledge, how they go forward from there. I probably am not going to have time to get around to that. Let's see, your second question, I was going to explain why we're not going to do that either. Remind me what the question was.
Interaction with other intelligent.
Oh, yes, well that was really the point, no, the other direction. That's really what we're talking about here. So the first thing is to be able to predict the behavior of other agents in terms of hypotheses about their goals and beliefs, and you can use observed actions to infer goals and beliefs, and then go on to do some of these things. Now, obviously, interacting with other agents, including learning to communicate with other agents and learning to align knowledge representations with other agents, is a huge, huge field and undertaking, and I think there's quite a lot of people working on it. So,
if I remember correctly, the system does learn that there are some objects that move independently. There's certainly some objects that move and some that are stationary.
yes. Well, no. Actually, all it does is it distinguishes between things that have ever moved and things that are always static. It doesn't actually learn to represent knowledge about whether things move independently. Now, this actually is something which I can fairly easily see it would distinguish between, but in fact it doesn't. Okay, well, thank you for this.